Okay, so I'll start roughly just burning through some slides explaining Sintef. This is some promoting material. Of course, this does not represent my day. You know how it looks. It's a desk with a huge screen and a laptop in front of it, and also a keyboard. But Sintef is one of Europe's largest independent research organizations. Thank you. Backwards or forwards? Yeah. Normal arrows. And Sintef Energy Research is an institute within the Sintef umbrella, which focuses on energy, basically. And instead of spending time listing areas, it's basically energy minus nuclear. Sintef itself is quite large, and we do tons of projects nationally and internationally in EU. And this is like the world image seen from Sintef. It consists of Sintef, universities, and industry. So this is like how we typically work. This is the vision for Sintef. And you can see we have activity in a lot of different fields. And we are now concentrating with the top left or the middle left top part of this butterfly. So we are on the border of societal benefits in the energy system, but also we have a very close connection to the industry with the energy part. So energy and digitalization is where we're living in. Now we'll just go through a crash course of energy system modeling, so you know a little bit about what we are working with on a day-to-day basis and what's the problem. If you don't know, like I did not know this existed before I started working with it, so I will completely understand if you don't know this. But the energy system works all the time, every day. And it's run by transmission system operators, which operate them. So here it's in Norway, it's Statnett, Sweden is SVK, here it's Energinet DK. And then you have power producers, which actually create the power. And then all of this is together in the power market, decided how much power is produced when and at what price. And there are also consultants which can do part of this work, and there's also regulators for each region that make sure that everything works perfectly fine and the market is obeyed and everything. And when this system is safe and stable, all of the generators work together in synchronicity so that everything, the load is distributed equal, the supply meets the demand at every time, and that's fine. That's a perfect condition. 60 hertz, super. However, deviations can cause overload of transmission lines or generators and can lead to blackouts and breakdowns of system, property damage, loss of life. Imagine the hospital, everything can lose power. It's very important that this works. Power market basically consists of futures, day-ahead, intraday, and balance markets. Nord Pool, just to give you like a size of the system, I did some back-of-the-envelope calculations for a few years ago. Day-ahead is the largest of these markets, like financially. So I don't know if many of you have seen a giga euro. It's a little bit bigger than the normal euro. Oh, I'm kidding, of course. But it's a lot of money going through every year. How it works is that the producers provide production bids, which is like volume at a certain cost. The market is cleared altogether, making sure that the supply meets demand, and then the TSO verifies the result, and it's operational security. This is a timeline of the day-ahead market. And we are interested in this part. So these are the 2 hours every day that the TSO publishes the constraints, like the boundary conditions for that day. They are locked, or they're published 10 o'clock. And then you have until 12 o'clock. 12 o'clock the market closes. And then you have to have all of your bids prepared. Every day, no exceptions. Christmas, New Year's, doesn't matter. This is how it works. And that will be important later on these 2 hours. This gives you like an operating window. Hydropower complicates things a bit because even though water is free, it just falls from the sky, literally. It has a value because it's an alternate cost of producing now or later in the future. And you have to balance this so that you ideally produce when the price is high. And you have to avoid flooding. And you also have different restrictions. And these restrictions can be environmental restrictions for like salmon rivers or political, like recreational, lots of different restrictions. And the value of water in any reservoir at any time is given, it depends on the value of, or the amount of water in any other reservoirs. And when you have 1,000 reservoirs-ish in Norway, this becomes a large-scale stochastic optimization problem. And basically, to act in this market, we at Sintef have a rather unique model suite that consists of, it's basically trying to create a map of the future estimated power price. And you want to look far in the future to be sure that you catch all of the different things that can happen. And the closer you come to the present moment, you want finer and finer and finer detail. So you typically have a large-scale model that calculates like the broad price estimates, and then you go finer and finer and finer. And we have examples, or we started this HPC adventure with the kind of the smallest model, just so you know that. Models are developed through industry-funded research and development, and has been built up over decades, and it's very much regulated with close contact with industry and requirements. So this is sort of like the part of this world triangle that we live in. And this has been driven by software research and development and industry requirements over time. We started in the end of the 60s. So this is very different from something that you would just go and buy in the street. And it's important for us, or like essential for us, to be part of we're defining the research front. So we have to be focusing, always looking ahead of like different changes to the market. They can start a different clearing process, developments in algorithms, development in technologies. So we have mostly been working on CPUs, but we have prototypes using GPUs. We're involved with the project now on looking into the future potential of quantum. And a little bit about how we get to HPC, or how we got there. Even though industry has been mostly Windows-based, it's now shifting like a trend towards Linux for different reasons. And we already had, we started when the computers were the size of different, or several tables, and punch cards were how you program things. So we had lots of iterations and working on things that work now and also for the future. And then we've also done several in-house improvements. You can see in the bottom here, which is almost a requirement. At least it makes it much more easy to get help to bring outsiders on board. If we have an onboarding process of years, it's quite difficult to get help. Which brings us over to help. So we have gotten a fair bit of help from Sigma 2. Sigma 2 is, for those who don't know it, they are responsible for the national e-infrastructure in Norway. And they also represent Norway in international projects such as the EuroHPC and the NCC. The NCC is a partnership between Sigma 2, Norse, and Sintef. And they have listed several success stories here, which I'm not going to talk about, but you can come find them outside here and ask them some questions. I'm talking about our journey and our collaboration with Sigma 2 and NCC, which has given us access to HPC experts and compute resources for us to test, and assistance in adapting code for large-scale HPC usage, which is sort of a requirement, because even though you think your code is completely ready to run on a big system, that's not necessarily true. And to get ahead of the final conclusion, what we have started, we have run something. I'll show you some example. But there's lots of future work going here. So we're going to continue running, analyzing, looking at some bottlenecks, and there's a lot of potential to improve on what we have seen so far. And there's also a really interesting path of using this, using HPC to try to provide to industry our software as a service, depending on pricing and future, and also interest and regulation, because our customers can be really small. Maybe there's one person in the IT department, or they can be large. There could be 150 people in the IT department. So it could be very interesting for the industry to be able to use this in an efficient manner. So at first look, this graph may not look fine, but this is fine, and I'm going to tell you why. This represents solution time, or the estimated efficiency for our smallest model that we've run so far. What's cool about this is that it's realistic. This is based on an actual data set that a customer would or could run if he could run it by himself. And this model and data set also is limited to 350, so there's definitely 0 at that point. But the point is that it can scale quite good, and you can reduce the wall time drastically. And if you remember back to my figure showing that you have 90 to 120 hour operating window, if you can use all of that window, if you have to use all of that window in one simulation, or you can do 60, 100, that gives you a lot of possibilities. You can just like imagine. I mean, what would you do? Would you do high resolution, or would you like to do like a scenario analysis that you couldn't do before? So there's lots of different things that you can try. And there's also there's an actually human side to this also. I mean, like I said, this power system runs every day, so it can actually give Kate, for instance. Maybe Kate doesn't have to be working on Christmas Eve. She can be home with her kids, because the simulation now takes 2 minutes. So they don't have to have, her company doesn't have to have like a watch system where somebody has to restart something that failed during the night, which could of course happen. So I got a quote from one of our customers, which is basically, this is important. And it is important because it gives you lots of different options. How you use it, it's how you, well, like I said there, it's the availability and scalability sets almost no boundaries. So this is going to be a very interesting future, and I'm really looking forward to running more systems and working more together with Sigma 2 and HCC to see where we can actually end up. And that would only be the first model. Then we can try the bigger model, and then we can try and then we can try. So it's, I think the potential is really, really interesting. Black screen. Okay.
Here we are.
Yes, I think that's fine.